Welcome to my channel. In this video, I want to discuss about Spanning Tree Protocol or STP. A key characteristic of a well-built communications network is its resiliency. A resilient network is capable of handling a device or link failure through redundancy. A redundant topology can eliminate a single point of failure by using multiple links, multiple devices, or both. STP helps prevent loops in a redundant switched network. Without STP, redundancy in a switched network can introduce these three issues. Broadcast storms. Each switch floats broadcast endlessly. Multiple frame transmissions. Multiple copies of unicast frames are delivered to the destination, causing unrecoverable errors. MAC database instability. Instability in the content of the MAC address table results from different ports of the switch receiving copies of the same frame. STP is an IEEE standard defined as 802.1d. STP places certain ports in the blocking state so that they do not listen to, forward, or flood data frames. STP creates a tree that ensures that only one path exists for each network segment at any one time. If any segment experiences a disruption in connectivity, STP rebuilds a new tree by activating the previously inactive but redundant path. The algorithm STP chooses the interfaces that should be placed into a forwarding state. For any interfaces not chosen to be in a forwarding state, STP places the interfaces in blocking state. Switches exchange STP configuration messages every 2 seconds, by default using a multicast frame called the Bridge Protocol Data Unit or BPDU. Blocked ports listen for these BPDUs to detect whether the other side of the link is down, thus requiring an STP recalculation. One piece of information included in the BPDU is the bridge ID. As you see the diagram, the bridge ID is unique to each switch. The bridge ID value is 8 bytes. It consists of priority value 2 bytes and the bridge MAC address 6 bytes. Why do we need spanning tree? What is a loop? And how do we get one? Let me show you a clear example. In this diagram, we have two switches. These switches are connected with a single cable, so there is a single point of failure. It means if the interface between two switches is interrupted, the connection will be down. To get rid of this single point of failure, we will add another cable. With the extra cable, we now have redundancy. Unfortunately for us, redundancy also brings loops. Why do we have loop in this scenario? Let me describe it to you. PC1 sends an ARB request because it is looking for the MAC address of PC2. An ARB request is a broadcast frame. Switch 1 will forward this broadcast frame on all its interfaces except the interface where it received the frame on. And switch 2 will receive both broadcast frames. Now, what does switch 2 do with those broadcast frames? It will forward it from every interface except the interface where it received the frame. This means that the frame that was received on interface fast Ethernet 0/0 will be forwarded on interface fast Ethernet 1/0 and fast Ethernet 0/2. The frame that was received on interface fast Ethernet 1/0 will be forwarded on interface fast Ethernet 0/0 and fast Ethernet 0/2. Do you see where this is going on? We have a loop. Both switches will keep forwarding over and over again until you fix the loop by disconnecting one of the cables or one of your switches will crash because they are overburdened with traffic. Ethernet frames don't have a TTL or time to live value, so they will loop around forever. Besides our request, many frames are broadcasted. For example, whenever the switch doesn't know about a destination MAC address, it will be flooded. How spanning tree solves loops. Spanning tree will help us to create a loop-free topology by blocking certain interfaces. Let's take a look at how spanning tree work. Here is an example. We have three switches, and as you can see, we have added redundancy by connecting the switches in a triangle. This also means we have a loop here. I have added the MAC addresses but simplified them for this example. See, switch 1 MAC address, switch 2 MAC address, and switch 3 MAC address. Since spanning tree is enabled, all our switches will send a special frame to each other called a BPDU. As I said, Bridge Protocol Data Unit. In this BPDU, there are two pieces of information that spanning tree requires: MAC address and priority. The MAC address and priority together make up the bridge ID. The BPDU is sent between switches as shown in the diagram. See? Spanning tree requires the bridge ID for its calculation. Let me explain how it works. First of all, spanning tree will elect a root bridge. This root bridge will be the one that has the best bridge ID. The switch with the lowest bridge ID is the best one. By default, the priority is 32,768, but we can change this value if you want. So, who will become the root bridge? See the bridge ID? Lowest bridge ID is the best one. In our example, switch 1 will become the root bridge. Priority and MAC address make up the bridge ID. Since the priority is the same on all switches, it will be the MAC address that is the tiebreaker. Switch 1 has the lowest MAC address, thus the best bridge ID, and will become the root bridge. As you see, the switch 1 has been elected as the root bridge, and now we have agreed on the root bridge. Our next step for all our non-root bridges means every switch that is not the root will have to find the shortest path to our root bridge. The shortest path to the root bridge is called the root port. Take a look at my example. D on the interfaces stands for designated port. Every port on the root port will be designated port. I have put an R for root port on switch 2 and switch 3. Their fast Ethernet 0/0 interface is the shortest path to get to the root bridge. In my example, I have kept things simple, but the shortest path in a spanning tree means it will actually look at the speed of the interface. Each interface has a certain cost, and the path with the lowest cost will be used. Here is the interfaces and their cost. Okay, we have designated ports on our root bridge and root ports on our non-root bridges. We still have a loop, however, so we need to shut down a port between switch 2 and switch 3 to break the loop. So which port are we going to shut down? The one on switch 2 or the one on switch 3? We'll look again at the best bridge ID. As I said, bridge ID equal to priority plus MAC address. Lower is better. Both switches have the same priority, but the MAC address of switch 2 is lower. which means that the switch 2 will win this battle. Switch 3 is our loser here, which means it will have to block its spot, effectively breaking our loop. Well, that's all we have for you today. Thanks for watching. If you like this video, please subscribe my channel.